Okay, in this section we're going to look at the graphs of the sine and cosine functions. This is section 6.4. So far we've been doing calculations with the trig functions with an angle theta and making triangles and working with the unit circle, but now we want to look at the graph of the trig functions on the xy plane. So let's start with y equals sine x. And now in the book, you might see the words independent variable and dependent variable. Okay, the independent variable is x, the dependent variable is y. So I've got some triangles set up here along with the unit circle, and I'm selecting values for x and plotting points on the graph. So like if x is 0, sine of 0, remember that whenever the angle is one of the major angles, we're using the unit circle. Sine of an angle is defined to be y over r, so y is 0, r is 1, 0 over 1 is 0. So here's 0, 0 on the graph. If I let x be pi over 6, here's my 30, 60, 90 right triangle. And the opposite side is 1, the hypotenuse is 2, so sine pi over 6 would be 1/2. Now pi over 6 would be 1/3 of the way from 0 to pi over 2, and so I've got that point and that next point plotted there. If I let x be pi over 2, that's one of the major angles, and so y is 1, r is 1, 1 over 1 is 1. Here's pi over 2, 1 on the graph. If x is 5 pi over 6, I've got a 30, 60, 90 right triangle, but it's in quadrant 2. Opposite over hypotenuse, I'm getting 1/2. So here is 5 pi over 6, 1/2. If I let x be pi, then y is 0 and r is 1. 0 over 1 is 0. Okay, so here's pi 0 on the graph. If I let x be 7 pi over 6, here's a triangle that is in quadrant 3, 30, 60, 90. The opposite side is -1. Hypotenuse is 2, so -1/2 would be the output there. Here's that point. If I let x be 3 pi over 2, then y is -1, r is 1. -1 over 1 is -1. Here's that next point. If I let x be 11 pi over 6, then here's my 30, 60, 90 triangle in quadrant 4. The opposite side is -1, hypotenuse is 2, and so I'm getting -1/2 for the output there. And then if I let x be 2 pi, that I've made one complete revolution around the center, and so I would get the same value as I was getting when x was 0. Okay, now one of the things that we learned about in the last video was that all 6 of the trig functions are periodic. The periodic factor for the sine function is 2 pi radians. So what I see here on the interval 0 to 2 pi is going to repeat. Okay, here's pi over 2, 1 on the graph. Well, if I go 2 pi radians beyond that, so I'm at 5 pi over 2, I'm also going to be plotting a point at a height of 1. Here's 3 pi over 2, -1. If I go 2 pi radians to the left, that'll put me at -pi over 2, and I'm also going to be at a height of -1. Okay, so the curve is going to repeat itself, what we see here on the interval 0 to 2 pi. Some properties of the sine curve. So the domain is all real numbers. I can let x be anything I want here, and of course I'm going to cover the entire x-axis. Now there should be arrows at both ends here, indicating that this curve is going to repeat itself infinitely often. The range, okay, so we see that on the y-axis we're ranging from -1 to 1, including those endpoints. You're never going to have an output that is going to be outside of -1 to 1. The function is an odd function. We looked at that in the last section, and so what we could take away from that is an odd function is always symmetric to the origin. I didn't use any symmetry here in graphing this, but this graph would be symmetric to the origin. And the intercepts are going to be infinitely many points here that would cross the x-axis. So here's 0, 0, pi 0, 2 pi 0, 3 pi 0, etc. Also in the negative direction, -pi 0, -2 pi 0. Okay, you'll have infinitely many intercepts to list. Now, of course, we could also use what we know about transformations. Okay, if I've identified y equals sine x as a basic function, then of course I can produce many more curves. So like here, if I want to graph y equals sine of x minus pi over 4, that would be a horizontal shift to the right of pi over 4 units. Okay, so all these points would have to go to the right pi over 4 units. Here's a couple of points that are on the original graph. Pi over 2, 1. When you go to the right pi over 4 units, that'll put you at 3 pi over 4, 1. Here's pi 0. When you go to the right pi over 4 units, that'll put you at 5 pi over 4, 0, etc. Okay, here's another equation. If we want to graph y equal negative sine x plus 2, the negative means that we're going to have a reflection about the x-axis, and then the plus 2 means that we're going to shift up 2 units. So I would be doing those two things on this basic function here. And here I've selected a couple of points that would be on the original graph, and here's where they would be going on the new graph then. Negative pi over 2, negative 1. When you reflect about x, that'll put you at negative pi over 2, 1. And then you're going to shift, let's see, it was up 2 units. Okay, so that'll put you at negative pi over 2, 3 on the new graph. Sorry, I'm pulling this up and down here. 0, 0 is on the original. Reflecting about x isn't going to change anything. You're just going to simply shift that up 2 units, though, so that'll be at 0, 2. And then here's pi over 2, 1 on the original. When you reflect about x, that'll put you at pi over 2, negative 1. Shift that up 2 units, and you'll be right back to the same point that you started off with there at pi over 2, 1. Okay. And these weren't any special points, you know, they're just kind of randomly selected just to see where we can see where those new points would be going then. Okay, and here's y equal cosine x. So same deal, I'm just using a table of values, and I've already got some triangles set up here for some values that I've selected in the table for x, and I've also got the unit circle for when I'm selecting the major angles. So like if x is 0, cosine of an angle is where I take x over r. X is 1, r is 1, 1 over 1 is 1. Okay, so here's 0, 1 on the graph. If x is pi over 3, then I've got a 30, 60, 90 triangle set up here. I'm using a 60-degree angle, of course. And adjacent over hypotenuse would be 1/2. Okay, so pi over 3, 1/2, that'd be where this point is located. If x is pi over 2, then I'm on the major axis here, and x is 0, r is 1, 0 over 1 is 0, so here's pi over 2, 0 on the graph. If I let x be 2 pi over 3, then I'm working with a 30, 60, 90 right triangle, but it's in quadrant 2. The adjacent side is negative 1, since you're going to the left of the center. Hypotenuse is 2, so negative 1/2 would be my output there. If x is pi, we're right here at this point on the major axis. X is negative 1, r is 1, negative 1 over 1 is negative 1. And so here's pi negative 1. If x is 4 pi over 3, I've got a 30, 60, 90 right triangle, but it's in quadrant 3. The adjacent side is still a negative 1 there. Negative 1/2 would be my output. So here's that point. If x is 3 pi over 2, then we see it's going to be 0 over 1 is 0. So we'll have an intercept there again. If x is 5 pi over 3, here's another triangle. The adjacent side is 1, hypotenuse is 2, and so 1/2 would be my output on that. And then finally, if x is 2 pi, I've made one complete revolution around the center, and so I'll be getting the same as output as I did when x was 0. So 2 pi 1 would be on the graph. Now, the cosine curve is also a periodic function of period 2 pi, so what I see here on the interval 0 to 2 pi is going to repeat infinitely often. And so I've got some additional points plotted here. Of course, I don't have a start-stop thing going, right? There really should be arrows on both ends. since you're going to cover the entire real number line. The domain of f is all real numbers. The range of the cosine curve is ranging from -1 to 1, including the endpoints, just like with the sine curve. The cosine function is an even function. We saw that in the last section. An even function is symmetric to the y-axis. I guess I could have used that here. I see that this curve is symmetric to the y-axis. If I were to list all the intercepts, there'd only be one y-intercept, 0, 1. You're going to have infinitely many x-intercepts. They're going to be at pi over 2, 0, 3 pi over 2, 0, 5 pi over 2, 0, 7 pi over 2, 0, etc. And then also at negative pi over 2, 0, negative 3 pi over 2, 0, negative 5 pi over 2, 0, etc. Okay? And again, we can use what we know about transformations. So like if I want to graph y equal 2 times cosine x, that would be a vertical stretch by a factor of 2. How I would get the new graph is I'd start with the original graph here, and I would multiply all the y values by 2. Okay, so here's a couple of points that were on the original graph. 0, 1, when you multiply the y value by 2, that'll put you at 0, 2. Pi over 3, 1 half, that was right here. Multiply the y value by 2, that'll put you at pi over 3, 1, okay, etc. I've got a couple more points there. Now, based on what we see here with the sine and cosine curves, with the cosine curve, if you were to shift this graph to the right, pi over 2 units, you would have exactly the same curve as the sine curve. So one way to look at how the sine curve is formed is sine x is the same as cosine of x minus pi over 2. You're shifting the cosine curve to the right pi over 2 radians. Okay, and I'm going to stop right there.